elaborate Monte Carlo and molecular dynamics simulation. Let's welcome the speaker.
Thanks for the Chairman's introduction. Good morning, ladies and gentlemen. It's my great pleasure to make this presentation today. I'm Tu Sun Ho. I'm a master student from the National Sun Yat-sen University in Taiwan, and this is my title of the study: observing the structural and material properties of two-dimensional supramolecule by hybrid Monte Carlo and molecular dynamics simulation. First, and this is my outline of my presentation. First, I will introduce my background and motivation, and I will show the simulation method in this part, and I will discuss the result in detail. Finally, we'll make some conclusion in this study. So, two-dimensional, we call 2D supramolecule materials, are currently very popular materials. Supramolecule were formed by the weak interaction forces, such as van der Waals forces, to arrange the molecules on the 2D substrate in a specific arrangement. 2D substrate can be applied to like drug delivery, as shown as this figure below. The 2D substrate can be used in a lot of fields, such as two-dimensional graphene analogs we call 2D GAS. It has similar structures and properties as graphene, and it can be used for like drug delivery, gene delivery. So we use graphene as our substrate. Supramolecules can consist of only two or more molecules. Many studies use the fatty acid or benzene dicarboxylic acid as examples to build the supramolecule. But in many studies of the self-assembly, it doesn't explicitly to discuss the influence of a process condition of the self-assembly structures. So we use the molecular dynamic simulation to investigate the effect of the different copy ratios and temperatures on the formation of the self-assembled structure. So we choose the stearic acid we call STA and the terephthalic acid we call TPA as our example to construct the 2D supramolecular self-assembly structures. During the simulation, the driving force field was adopted to simulate the interaction between atoms, and the atomic partial charge was obtained by the electrostatic surface potential charge of a semi-empirical PM6 calculation. This is the flow chart for obtaining the most stable structures in the 4 different coverage ratios. First, we deposit the different numbers of the STA molecules on the same size graphene. Like this figure is for 80 STA molecules on this size graphene. So we apply to the external forces to make the STA molecules to work to absorb on the substrate, and we will have to make sure that STA's molecules are absorbed on the substrate totally. Then we use the hybrid Monte Carlo method, we call it HMC, and we use the MVT ensemble and do the 100,000 loops, and the temperatures is decreased from 600K to 300K. And after that, we'll get the most stable structures on the different coverage ratios. And finally, we have been some further analyzed by the MD simulation. And this is our HMC method flowchart. First, the STA will randomly place on the graphene as the initial structures. And we will use MD to make the STA molecules to moving around. After that, we use spacing hopping to find the global minima configuration, and we will save the stable structures every time, and we'll repeat this process for 100,000 times. Finally, we will obtain the global minima configurations at this procedure. So this full coverage is the most stable structures after the HMC method. The right table on your right-hand side is the intermolecule binding energy for each STA molecules in a stable state, and for the different coverage ratios. So after we get the most stable structures after the HMC method, and we have to make sure about their thermal properties. So these figures show the square displacement we call SD for the different coverage ratios and the different temperatures. So during the simulation, the template has 10K increase for each time from 300K to 600K. And these curves, these four coverage curves, were plotted by all of the atom trajectories and during the whole MD simulation process. And we can observe that at the specific temperatures, like this one, this one, this one, this one, and it made STA move significantly, and such as STA in the 400K, STA 100 in 420K, STA 130 in 480K, and STA 140 in the 510K. So we define these temperature as the decomposing temperature. This figure is the mean square displacement we call MSD, and for the different coverage ratios are the constant decomposing temperatures. So the MSD was calculated by the all-of atom trajectories during the 400 picosecond MD simulation process, and all of the trajectory displacement were averaged by the 8,000 total data. So from this figure, we know the magnitudes of the displacement for the four different coverage ratios at the decomposing temperatures can be observed. So we can see that in the STA80 for the black line had the biggest magnitudes variation of displacement. So that is because that in the STA80, this coverage, it has the most space of activity is much larger. So on the contrary, STA 130 for the green line and STA 140 from the blue line is relatively small, their space of activity. Okay, so this is the order parameter we call OP. It's the degree of the order for the STA molecules. So OP it will become order as its value approaches to 1. And we can see that when the temperature rises, like these figures, in different coverage, when the temperature rises, the stable structures were distorted. So after that, when the order parameter is getting lower, when the coverage ratio is more higher. So we can reveal that in this figure is OP has a tendency to rise first, then decrease, like STA 100 and STA 130. So that is because the hydrogen bond had a directionality in the stable state. So when the temperature rises, the stable state was destroyed, and the hydrogen bond will gradually lose their directivity. So the STA order will be more neatly until about the decomposing temperatures, the OP will drop in our decomposing temperatures in each case. We can observe that in the case STA 140 for the blue line, it doesn't have any obvious change in OP. And indicated that in this case, this coverage has exceeded the range can be carried by the graphene area as our examples. We saw the tendency that the OP rise first and decrease. So in order to verify our HMC works to finding the lowest energy and the stable structures, the average in every temperatures, average energy in the every temperatures will plot. And we can see that the result reveals that in the initial structures, it has the lowest energy. Okay, and in the right-hand side is the figure is show the equilibrium at the decomposing temperatures for the 50 picosecond MD before the MSD. And we can saw the energy is statistics that for all the carbon ratios at the decomposing temperatures have been already equilibrium. Then we do the MSD calculations. So this is our conclusion of my study. First, the carbon ratios affect the self-assembly structures and thermal properties of the three-dimensional supermolecule. Second, the HMC method is efficiency method to obtain the most stable absorption structures at the STA on graphene substrate. Third, the decomposing temperatures of STA 80, STA 100, STA 130, and STA 140 are 400K, 420K, 480K, and 510K respectively. And finally, the size of this size graphene substrates can be absorbed maximum around 130 to 140 molecules. Here we must first apologize to you guys that we didn't finish our supermolecule. So in the futures, we will use the same as STA method to put the TPA on the STA as the buffer layer and as our plan. So in the future, we want to develop a general proposed program as a template and to predict the general properties of all 2D supermolecular. So in the future, any self-assembly behavior can be performed only by changing the formulation of supermolecule. Finally, you have to thank the National Sanyashan University and the Ministry of Science and Technology of Taiwan. So this figure showed our lab member, and this one is our group leader, Professor Xunpeng Zhu. Thank you for very much for your attention.
Thank you. Any question? Yeah, sure.
Yeah, well, I use the LAMP package to do the MD simulation.
So what kind of potentials do you use?
The dreading potential.
Okay.
Yeah, because it is really suitable to our molecules and this system for supermolecule and polymer. Yeah.
So how about the graphene inside?
Graphene?
Yeah.
Well, we use dreading, also use dreading potential. Yeah.
Good.
Thank you.
Thank you. All right. So now let's move to the last speaker for this session, Mr. Ankush Kashua. He's from KIT, right? Yeah. So his talk is about in situ cyclic deformation studies of nanocrystalline palladium thin films using automated crystalline orientation mapping in TEM.